So the this is the same number written in three different bases. These are equal to each other. So 463 base 10 equals 111001111 base 2 equals 1CF base 16. Now the fourth number system we'll look at is referred to as octal. Octal is a base 8 number system. So that means we have digits 0 through 7. Anything above 7 is illegal as far as a digit goes. So I started counting in octal 0, 1, 2, 3, 4, 5, 6, 7, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Then we go 2, 0, right? 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 3, 0. And we keep going and going and going and going. What we do, though, is what we're trying to do is we're trying to come, we know that the binary number system is very cumbersome. And the longer the number of bits that we have, the more complicated it is for the computer to, the computer can display it accurately, but our brain has the tendency to run things together, right? You understand that? And it's trying to convey it to it accurately. So in the base 8 number system, 8 to the first, we have exactly 8 combinations, 0 through 7. With 3 bits of binary, we have exactly 8 combinations, 0, 0, 0, 0 through 0 to 1, 1, 1, 1. Okay. So what does that mean is we can use 3 bits of binary to represent each octal digit. So it's almost like hexadecimal, but instead of splitting the binary number into groups of 4s, we come up and we split the binary number into groups of 3s. 1, 2, 3, 1, 2, 3, 1, 2, 3. Then we write down the digit that represents those groups of 3s. So this will be a 7. This will be a 1, 7, and this is base 8. So it's basically the same as hex, but on octal we use groups of what? 3s. On hex we use groups of 4s. Now this computer does not use the octal number systems, but PLCs it's available. So when you get to doing logic and stuff like that, or bit manipulation, it's up to you as a programmer to decide which base you use. And it's pretty easy on the Arch Logic 500, and it's not hard on your more advanced operating systems. But we'll show y'all how y'all can do that, even on the new number systems. And I'll give you all a list of the approved number systems in the range. So if I was to have a decimal number, 387, 384, I want to take that to binary. So y'all convert that to binary for me. To binary, not octal, not hex, to binary. So what's the first thing we're going to do? We're going to lay out our chart, right? 1, 2, 4, 8, 16, 32. And hit record. So this is taking the decimal number and converting it to binary. If I was going to go to hexadecimal, I would come in and I would split this up into groups of 4, starting with the least significant bit, 1, 2, 3, 4, 1, 2, 3, 4, and then we'd write down the equivalent, right? What would that be? That'd be 1, 8, 0, base 16. If I was going to do that in octal, I do exactly the same method, but I come up here and split that number up into groups of 3s. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, everybody okay? So that would be a what? That'd be a 600 base 8. So what we're doing, so 384 base 10 is equal to 110 00000 base 2 is equal to 180 base 16 is equal to 600 base 8. So what we're doing is we're looking at the same number in 4 different number systems. So the only difference between going from base 2 to base 8 is we use groups of 3s, or going from base 8 to base 2. So if I had a base 8 number, 1573 base 8, I'd use groups of 3s. 1, right? 5, 7, 3. And then I've got it in binary. So it's real easy to go between these high-level number systems and binary, and that's why we use them. We don't use them to try to convert hex into decimal. We use it to we go hex to binary, right? Or we go from binary to hex. We usually don't go, if I was going to go from decimal to hex, I would go through binary, because I can do that without a calculator. I just lay out a chart, I subtract the highest power of 2, I can do it. And then once I got it in binary, I could very easily go to what? I could very easily go to hexadecimal. I could very easily go to octal. So that's the 4 number systems that you'll run into in PLCs. Now, fortunately, in this class, this is the guy we're going to be using. But we're still going to have to understand this when we talk about the range that we have available to us. So when we get into counters and we get into timers, we're going to enter that in decimal, but it's going to have a specific range of numbers that we can actually do, especially counters, because we can count up or we can count down. So we have to deal with negative numbers on that. Any questions on that, guys? Okay. I don't know if I got a chart counting in octal or not. So here's counting in octal. Codes. A code or a system of words, letters, figures, or other symbols substituted for other words, letters, or symbols. The codes that we use in PLCs, and this is going to really screw y'all up, we have what we call a binary coded decimal. So this is not a numbering system, this is a code. We have the gray code, which is a high-speed counting code. We have the American Standard Code for Information Interchange. That shouldn't be coded, guys. The D shouldn't be on there. In fact, while I got it up, I'm going to go up there and take it off. Oops. Oh, we call this an acronym. So technically, an acronym means you take a group of words, you take the first letter of the most significant words, then you use that to create another word. In computers, that's really slack. So we call SEC an acronym. Technically, we don't say SIC, right? So ASCII, this is pronounced ASCII. This is American Standard Code. EBCDIC, we don't use anymore. The book teaches this wrong. Okay, it's actually extended ASCII is what they have, and then we have what we call Unicode. This is what our computer uses. So binary coded decimal. This is not a weighting number system. This is a code. So this is what y'all were doing a while ago when you did it wrong. You were trying to go from decimal over to binary by using groups of 4s. This is what we do in BCD. It is not a weighted number system. It's a code. Each 4-bit binary numbers are grouped in to form a decimal number. 4-bit groups represent 0 through 10 numbers in BCD. So if I was this is going to give y'all problems because you're going to try to do this, and I'm trying to tell you, BCD is not a number system. It's a code. Some people call it the 1, 2, 4, 8 code. It don't go 1, 2, 4, 8, 16, 32, 64. It doesn't do that. It goes 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. So if I was going to go from decimal to BCD, 5,684 base 10. Now, if I was going to go to binary, I would go 1, 2, 4, 8, 16, 32, 64, 1, right? Y'all understand? I would subtract them. That's a weighted number system. BCD is not a number system. It is a code. It is not weighted. So if I was going to go to BCD, then we always use groups of 4s. This would represent the 5. This is not a numbering system. This is a code. This is not weighted. It's a code. This would represent a 5 in BCD. This would represent a 6 in BCD. That would represent an 8 in BCD. That would represent a 4 in BCD. It does not go 1, 2, 4, 8, 16, 32, 64. If you did it, and a lot of people call it the 1, 2, 4, 8 code. It does this. It goes 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. So some people call it the 1, 2, 4, 8 code. It is not binary. It is a code that we can directly represent each decimal digit. Somebody's going to go to binary by doing this. And you can't do that. Binary goes 1, 2, 4, 8, 16, 32, 64, 128, 256, right? You understand that? This is not a weighted number system. This is a code. So this is the way most computers represent decimal numbers right here. Most computers can actually do BCD math. They added that instruction to microprocessors a long time ago. And you got to do groups of 4s. So normally we separate them. Y'all see my spaces in there? This is not a number system. This is a code. It's in its name. Binary coded decimal. This is not binary. If I was going from that number to binary, then I would start off, this is going to be a big number. I'd go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, which we don't need. And then I would start subtracting, right? I would subtract the highest I could. That's a weighted number. So we're going from a weighted number system to a weighted number system. This is not a weighted number system. This is a code that we use to directly represent decimal numbers. Somebody in this class, I've never taught a class where I say convert the following numbers into hexadecimal, and they'll go to BCD. They'll split it into groups of 4s. They think it's that easy, and it's not. So what would be BCD? So what would be the number represented by this? You got to use groups of 4s. So by the way, that's illegal in BCD. I'm sorry. This is illegal in BCD. So what we're doing with BCD is we're sacrificing we're sacrificing 6 combinations. So there's no such thing as that in BCD. No such thing. The highest thing we have is this right here. That's the highest code that we have for a 9. So if I was going to represent a 10, I'd do this. I'd go 0, 0, 0, 1, 0, 0, 0, 0, and this would be BCD. This would be a 10 in binary, 1010. This is binary. This is BCD. This is a code. This is a weighted number system. Somebody in this class is going to do that. Somebody's going to go directly from they're going to go directly from decimal to binary, and they're going to use groups of fours. They'll go to BCD. So if I was counting in BCD, oops, sorry guys, I don't know what I just did. Erase it off. If I was counting BCD, this would be 0. This right here would be 1. This right here would be 2. This right here would be 3. This right here would be 4. This would be 5. This would be 6. This would be 7. This would be 8. This would be 9. This would be 10. That's why we counted BCD. It's not a weighted number system. It's a code. It's not a number system. It's a code. But it makes it real easy for us to represent these characters. So if I have this BCD number right here, my pen stopped working. This is going to be rough. So 6, 7, 9. 9. Page 10. What would that be in BCD? Very easy, guys. I mean, you got to do it in groups of fours. You usually split the groups out, right? So what would that be in BCD? Zero, 1, 1, right? 0, 7, 9. Is that a binary number? No, it's a code. BCD. It amazes me some people can do that with a mouse. So real easy, but the number is not weighted, right? You understand? It's a code. If you took that right number and converted it to decimal, if you go 1, 2, 4, 8, 16, 32, 64, there's no way in the world you're going to come up and get 259. 279. Everybody okay on BCD? So this is BCD, 3, 4, 5, 6, 7, 8, 9, and that's it. So binary to BCD, that's our combinations we have. We sacrificed 6 combinations in a weighted number system. The number of combinations, we already looked at this. The number of possible numerical combinations can be calculated by raising the number of the base to the number of digits. So base 10, 2 digits, I could have 100 combinations. That would be 0 through 99. The largest possible number you can calculate is the base raised to the number of digits minus 1. So if I have 2 digits of base 10, that's 10 raised to the second power. That's 100 minus 1. That means the largest number I can represent is 99. Because technically 0 has no weight. 0 has no sign. We can't assign 0 a sign, right? We can't make 0 a negative number, and we can't make 0 a positive number. 0 is just 0, which is pretty interesting. So y'all understand this? We'll use this later on when we start getting into timers and counters, when we understand the range we can count to. BCD is not a number system. It's a code. Can you go around the other way, guy? Guy, can you go in that other door over there? Please don't walk. I've got a class going on. You know there's a door over there, right? BCD is not a number system. It's a code. To convert a number from any other number system besides decimal, the BCD number must first be converted to decimal. Then represent each decimal digit with 4 bits of BCD code. It's a code. Notice I've put this down here in red several times. BCD is not a number system. It's a code. It technically has no weight. It's a code, right? Y'all understand that? Yes or no? Gray code. So when we count in binary, so if I was to count in binary, oh, dang it, I'm not gonna be able to do this. I think I got a chart. So if I was to count in binary, 0, 1, 2, 3, 4, 5, 6, 7, and when we start counting, how many bits had to change right here? From 0 to 1. 1, right? How many bits had to change right here? Well, this one changed to a 0, and this changed to a 1, so 2 bits had to change. When we count from a 2 to a 3, only 1 bit had to change. When I count from a 3 to a 4, 3 bits had to change. When I count from a 5 to a 6, 1 bit changed. I'm sorry. Yeah, 2 bits changed. When I count from a 6 to a 7, 1 bit changed. When I count from a 7 to an 8, 3 bits changed. So the problem we have with counting in binary is in digital, we have something we call a propagation delay. So a propagation delay is I have a program that's counting, and it takes time for the program to actually propagate through, right, to do the counting. So the problem we have is the more bits that has to change, the more propagation delay we have between the input and the output of the circuit. So what they did is they came up with a code called the gray code. The gray code is a code. The gray code is not a number system. The gray code is a code. But what they do on the gray code is, so this is counting in the gray code. So decimal 0 would, okay, that'd be 4 zeros. A decimal 1, how many bits changed going from a 0 to a 1? 1. When I count from a 0 to a 2, how many bits changed? No. 0 to a 1, we had 1. A 1 to a 2, I'm sorry, 1 to 2, how many bits changed? How many bits changed? Going from here to here, how many bits? Yeah, 1, right? Now, if I converted that to decimal, that would be a 3, but this is not a number system, it's a code. It's a counting code. I go to a 2 to a 3, how many bits changed? 1. I go from a 3 to 4, how many bits changed? 1. I go from a 4 to 5, how many bits changed? I go from a 5 to a 6, how many bits changed? 1. I go from a 6 to a 7, how many changed? I go from a 7 to 6, how many changed? 1. So no matter if we count up or count down in the gray code, every count only changes 1 bit. So gray code is a high-speed counting code. You can convert it, but you have to do something we call an exclusive OR. So normally, if you do gray code, you'd have to look it up in the chart. Most people look it up in the chart because it's a code, right? You understand that? Binary depends on which way you go. So here, when I go from a 16 back to a 15, then 4 bits had to change. Counting backwards. The gray code, it doesn't make any difference if you count forward or count backwards, only 1 bit changes. But it's not a numbering system, it's a what? Code. So odds are you'll have to look it up in a chart. It's not as easy as BCD. So this is gray code. This is what you do. See, I don't need to know that. Now, when I look at my screen, There's a lot of things up here besides numbers, right? So special symbols is not a number. But the computer has got to be able to display an uppercase S. And it's got to do that with binary. So what we have is we have codes that represent characters. The first code we used was called the ASCII code, the American Standard Code for Information Interchange. And this is what computers originally used. So it's a 7-bit code used to represent letters, the Latin alphabet, decimal numbers, characters, and control codes in a computer system. 128 to the 7th different combinations. Data is often sent in bytes, which would be groups of 8s. 8 bits and 8 bits in 1 byte of transmitted data can be used for a parity bit. The 8th bit, we'll talk about that. And I think I gave you an ASCII code chart, so I think it's going to be on the back of that numbering system chart that I gave you. This is what we use for. This is what we use by PLCs. PLCs use ASCII, and your computer uses a form of ASCII. So that means when my computer displays that A right there, when it sends that information to your video controller, it's got to send a binary number. The video controller don't know what an A looks like. What it's got a chart, and you send it a code, and that determines what bit pattern it uses. Anybody know the code that these use? You can see them. If I come over here, let me find my blank page right here. If we go to insert, and what I'm going to do is I'm going to insert. Oh, it's highlighted out. Good gracious. Oh, I know what I need to do. Let me bring up my no. Let's see if this works. Insert a symbol. And we'll look at more symbols. So I'm going to type on my computer on this thing. I'm going to type an uppercase A right here. Now, the computer, Microsoft Word has no idea what an A is because I've got to send it that information in binary. So, that's what it sees right there. What base you think that is? That's hex. Hex. And it's a code called what? Unicode. So when I type an uppercase A on my computer, that's the code it stores in the video memory right there. And then your video memory for that location has the bit pattern for the what? For the A. ASCII is, and if you look up the ASCII code for an uppercase A, y'all got your ASCII code chart? Look at column 4, row 1. What do you see? You see what? Column 4, row 1. Let me find my ASCII code chart. So handouts. Handouts. ASCII. Okay, so here's ASCII. Column 4. I think y'all's is in hex, right? 4. Is y'all's in hex? Okay. This is in binary. Column 4, row 1. What's there? Now remember, we start counting in zeros, right? So this would be column 0. This would be row 0. So column 4, row A, would be uppercase A. Everybody okay there? So that's what ASCII is. So ASCII is what we've seen. So if I want this display to display my name, I would send it the codes in what? ASCII, right? You understand that? So let's see if I can do my name. Y'all got y'all's charts there? So what would be the codes for my name? So uppercase R. Give it to me in hex. So I think y'all's charts lays out in hexadecimal. It makes it a lot easier. The ASCII code is a binary code, guys. But it's a lot easier if we do it what? So let me. So what's an uppercase R? Oh, I inserted an equation. What's the code for an uppercase R? Give it to me in hex. Dang it. Huh? Is it 5? Yes, no? That's the column, but you read column number, row number. So it can't be just a 5. It's going to be a 5, right? Then what's the second one? Is the column, is it in column 5? What's the row? What's that? 2. Okay, good. Oops. 2. I'm going to have to reset my computer here in a minute. Next time we're going to break. So this is the ASCII code for an uppercase R. What's the ASCII code for a lowercase I? 6 what? 6-9? Now what's the ASCII code for a lowercase c? What's the ASCII code for this is lowercase c. What's the ASCII code for lowercase h? 6-8? This is not a weighted system. This is not a weighted number system. It's a code, right? Of course, laying out the hex chart in hex is a lot easier than the chart I brought up, which is laid out in binary. But ASCII is a binary code. It's not a hex code. It's a binary code. So if I come up here, and like I said, this does not let me insert a symbol for some reason. And you can see the codes. Now it is. So you can literally see the codes here. Now notice Unicode, ASCII code is an 8-bit code. It's technically a 7-bit code, and we'll talk about that in a minute, which gives us 256 combinations. And not only do we have the ability to send characters, we also can send what we call control codes. So we got. I'm gonna display something. I got to tell my computer when it gets to the end to do a line feed. So we got a code for a line feed in there, LF. Y'all see that? We got a code for a carriage return, which tells not only do we have to do a line feed, we have to do a carriage return to bring it back to the end. And sometimes you can see this code when you look up when you display the source code for a web page. So a web page is by George is basically in ASCII. So that's the way we send it. Before Unicode came out. So before Unicode came out, all web pages were just ASCII. You wrote text, and if you wanted to do a carriage turn, you'd if it's going to be a unit, you'd put a %, and then you'd put the ASCII code for a carriage, the hex code for a carriage return, which was 20. And so if you ever look at the source code of a web page, you'll see those ASCII characters. And the way they do it to indicate a control code is they put a % in front of it. If y'all have ever looked at source code for web pages, can y'all still do that? I think you used to actually look at what we call hypertext markup language. The only problem is that the only problem we have is that ASCII code is the Latin alphabet. So when the internet first came out, all web pages were English. No matter where you was at in the world, web pages were English. So they knew they had to do something to come up with codes that the whole world could represent. So this is when they came up with what we call Unicode. Unicode varies, but the primary code is a 16-bit code. So with 16 bits, that means I've got 65,536 characters I can have codes for. So that's why the internet uses Unicode now. The lower 127 is ASCII though. It just puts zeros up in front. So if I was to come up here and look up a lowercase c, it's 63. So see, so they kept ASCII. So if they did away with ASCII, that means all these websites that were written around ASCII wouldn't work anymore. So the first 127 characters of Unicode is still the old ASCII code. And then after that, now we can do what? Look what we can do with Unicode. Not only can we do the Latin alphabet, but we can do the prominent languages that's out there. But your computer does not support all of them. I don't know if you've ever went to a website and it tells you need to download the character set. So if you go to a Chinese website, it might tell you need to download the character set. And what it does is brings down some ASCII codes. So this is Unicode. Unicode is used by the internet, and of course it's used by Microsoft applications. So by the way, this means this character set is not in there. So when you come up here and you type in the letter A, so I come up here and I type in uppercase A, then that's 41, right? You understand that? So everything we do has, so a code is when we use something to represent something. So if I display it on this computer, it's got to be binary. So we have codes. Codes are not weighted numbering systems. That's just what we do to represent things, right? You understand? So what's the number 5? Huh? 35, yeah. So, but that would be 0011, right? 0101. It's a code. So gray code, ASCII code, Unicode. So Unicode is what we're using now. Okay, so there's another thing they cover in the book. We need to understand what's going on. So what they wanted to do, and then we'll have a worksheet that we'll start in, guys. So I know y'all getting tired of listening to me talk. So these are control codes in the ASCII code where we can do start a text, end a text, start a transmission, end a transmission, line feed, vertical tab, horizontal tab, backspaces. And you can see a lot of this you do a lot of this you're doing on your keyboard, right? You understand? So everything we do has to be represented in binary by code. So when I come up here and tap on this keyboard and I hit this backspace key, it sends a code into my controller. By the way, this is not ASCII code. This is a key scan code that IBM came up with, and we can look at that. But it's a code. So there's a code, but you can see if I'm sending information, not only do we acknowledge, not acknowledge, we use that for handshake, which means I'll send a number out. If it don't match what I sent, then it'll send by the computer will send back a not acknowledge, and it tells me to retransmit that last character, right? Understand? Vertical tabs, horizontal tabs, form feed. So this is it's usually what you used to send to your printer to tell it to spit the paper out, right? So y'all do that a lot, right? Carriage return. I can't remember what SO and SI stands for. DC 1s, 2s, and 3s. These are usually hardware specific. So all these over here are nothing but control codes. And these are characters. Not only do we have the text, we've also got to have all our punctuations, right? Our commas, our exclamation marks. So we have code for all our punctuations that we use. And then, of course, the delete that tells it to delete when you hit that backspace or your delete key. It sends that code. IBM decided not to use the ASCII code. They developed their own code called a key scan code, and I don't know if I've got this in here or not. So what they did, so this is extended ASCII. Hold on a second. So what they did is they wanted to create a method where we could verify the data that was sent is the data that was received. So one of the first methods they used was something we refer to as parity. So what's the ASCII code for an uppercase A? Dang it. So what's the ASCII code for an uppercase A? 41? Good. Now the way it was is 41. So notice I'm only trying to use 7 bits. So what they wanted to do was coming up with a real fast method for the receiver to verify that it received what was sent. Because all we got is ones and zeros. All it does is it takes 1 0 to change one of the bits to change, and it would see it as a different character. So the first method they came up with, and it's still used today, is something called parity. Of course, parity means equality. So what you would do is you have 2 parities that you can set up, and your transmitter and receiver have to be both set up the same way. So you either set them up both for even parity, or you set them up both up for odd parity. Now, if I've got it even parity, so let's start off with even parity first. What the transmitter would do would count the number of ones. So how many ones do I have in this right here? 2 ones. Is 2 even or odd? It's even. So I'm sending even parity. So what my transmitter would do, it would put a 0 out here. So when it adds all the ones in the code, it would always come up even. So what would be the ASCII code for, what was this the ASCII code for? What's the ASCII code for number 5? What's that? Okay, so it'd be 3 5. So it'd be 0 1 1 0. No, what's 0 1? I don't want to. That's not gonna work. That's still even. So what's the ASCII code for number 6? 7. What's the ASCII code for number 7? Okay, that'll work. Number 7 is 337, right? Okay. So I'm going to send parity. I've got both of my computers set up to run even parity. Okay. And what it does when it transmits, it would count the number of ones in the code. So how many ones do I have? 1, 2, 3, 4, 5. So what the transmitter would do, it would set the parity bit to make the total number of ones in the 8-bit code always even. Does that make sense? So what would happen is the receiver would come up here and count the number of ones. If it comes up even, it strips off the parity bit and it says it's okay. If it's running even parity and it counts an odd number of ones, then it would probably send a NAC back to the transmitter and it would retransmit the data. Now, this is what we originally used on disk drives. They understood right off the bat that this was not this finds around 95% of the errors. But the information that I store on my hard disk or my mass storage devices, 95% is just not accurate enough. So what they do on that, they'll use something called a cyclic redundancy check, or CRC, and we're not going to get into that. So ASCII, parity, what do? We add an additional bit. Both your devices have to be set up for the same parity. Then the transmitter would always add a 0 or a 1 to always either make the transmitted number even or make the transmitted number odd. Number of ones, not the number itself is not odd. I need to get that back. The number of ones in the code would always be odd or even. Now we're going to run into that. Anybody ever used the device manager? Anybody ever used control panel? This is probably a control panel. So this is something that's you really need to learn to get control of your computer. If it's running Windows, on an Android system, I don't know, but if you got a computer running Windows, then this is something you need to become familiar with. If I can get it to come up. I keep a shortcut on mine. I use mine so much. Control panel. Okay, so this is control panel. Most people, when it pops up, it'll come up to categories. It'll come up like this. What I do is I come up and change mine to small because it shows everything. So if you want to display your file extensions, I'm going to go to this guy right here called System. And then I'm going to go to Device Manager. This is all the devices on this computer that's being managed by my operating system. Now, as soon as we install our PLC, this cable that we connect to our PLC with, so this is cable right here. This is what we're going to connect to our PLC with. Okay. It's running off a USB port, but it converts it over to what we call an RS-232 port, which we call the COM port. So as soon as I install this on my computer, we should pick up a COM port right here. So see the COM ports right there? And then I'm going to look at COM port 8. And this is something we're going to have to do. Our computer uses what we call plug and play. And plug and play means it assigns addresses to devices that have that feature. So can y'all see what mine is assigned to? Can y'all see that? COM8. Okay. And look at some of the settings that's available to me. So port settings, I can set the bit speed. So this guy runs at 9600 bits per second. I can set the number of data bits, and then I can establish, can y'all see that third thing down there? What does that say right there? Parity. What parity am I using? None, right? But here's where you got even, odd. You can always transmit a 1 as parity or you augment. So this is where you'd select even or odd right there. So we'll have to understand that. The big thing we're going to have to understand is this guy right here. What COM port does Windows assign that to for your PLC? Are we okay so far? Any questions? Okay. Anybody sleeping? Hope not. So parity. So when I come up here and load up my PLC, first of all, we got, so all Allen Bradley PLCs, no matter how they're used, you have so many methods of communicating with the PLC that the first thing you got to do is make sure that you have the right driver installed. So what's a driver? Nobody in here knows what a driver is. Y'all should know that, right? What's a driver? So we have an operating system. What does an operating system do? It makes the computer operate. It's made of thousands of drivers. So a driver is a little old small module that is specifically written to control a piece of hardware. So I've got a driver for my video. I got a driver for my hard drive. I got a driver that runs my sound. I got a driver that does this. I got a driver that does that. Every once in a while, when you insert a USB device in there, it says loading software. Well, what it's doing? It's loading the driver to make that work, right? You understand? Because the operating system doesn't support that device. If you cancel out, then you're not going to be able to use that device. So a driver is a specific piece of it's a module. It's a program module that's specifically written to control a piece of hardware. So we got video drivers. We got, USB drivers. So when I come up here and I insert my mouse, and when I inserted my little Bluetooth thing to run this mouse, it had to do what? It had to install a driver because it didn't support that. Luckily, PNT usually does that for you. The driver we're going to use is this. So what I would do is I would come up here first, and I would go to communication, and then I would come up here and configure driver. And what I need to do is find the driver that my PLC communication supports. We're using this DFI 485 driver is what we're using. And then when I come up here and hit configure, what is it asking for? First of all, it's asking for the COM port. So if we don't know the COM port, then the driver's not going to work. So I found that in Device Manager. It told me it was on COM port 8. So right up here, what did I do right off the bat? I came over here and used this scroll box, and I went to COM port 8. By default, it's not going to find it. It don't know where it's at. So we can find in Device Manager when we plug that thing up what COM port it's assigned. Then it says I need to know the baud rate. 19.2 says it's using cycle redundancy code. It's not using parity. It's got one stop pit. Full duplex is basically communication in both directions. Do I have to know this? No. You notice I've got something right here. You see what this says? Auto configure. So if you've got your COM port selected right, you can come up here and tell RS Links to come up here and configure the port, and that's all there is to it. So it automatically went in and set all that information up there for us. But basically now we have a basic feel of what it's doing, right? It says it's successful. So now when I go in and so no, we're not using parity, but we know what parity is, right? So RS Link. So if I go out and install a Compact Logic PLC, a brand new Compact Logic, the first thing I'm going to do is run RS Links, and I'm going to load in the right driver, and then we're going to configure the driver, right? Now once we got the driver, so I'm going to come up here and click on that. There's my PLC right there. So I'm ready to go. I'm ready to go to work. So now I can launch the application, which I'm going to have to fix on y'all's. And then once we launch the application, it should come up. And then when I go to comms and I see who's active, then there's my PLC right there. Okay, so now we can program that. And now we're ready to program our PLC. So this is what's actually in the PLC, by the way. And this is where we'll end up right here, working with timers. So this program has 7 rungs in it. This end is automatically put in there for you, so we can't put any control devices in the end rung. So your first rung will always be 0. So when you start off, the end will be 0, and every time you insert a rung, the very top rung always comes up in the 0. So what type of? Oh, we hadn't talked about logic in here, have we? Okay. So any questions so far? Let's see what else is in here. I think that's about it in this PowerPoint. So what we'll do after this is I'll give out a worksheet. ASCII, y'all okay on ASCII? Okay. Talk about control code. What they did is they added an extended ASCII set, and this is what the book calls EPSODEC. EPSODEC is this is EPSODEC right here. So this was IBM when they first came out with their mainframe computers. They knew they had to have a code, extended binary code. I can't remember what the acronym is. So IBM came up with this code. This was a proprietary code. So the only people that could use this code was what? Was IBM. So the code in your textbook that says it's EPSODEC is not EPSODEC. The code they give you in your book is what we call extended it's called extended ASCII. Let me find it. Yeah. So this is extended ASCII. And what they did is basically it's what we use for graphics. So it added a bunch of graphics characters. It added some English. It gave us the ability to draw boxes on the screen. It gave us the ability to do this guy right here, Omega 235. I can't do it on this computer, but you can get on any IBM computer and like you're doing Microsoft Office, and you can hit the Alt key and enter 235 on your keyboard, and the Omega sign will pop up there. So you can directly enter, and you can directly enter Unicode too, but I can't remember exactly the syntax. This computer don't have a numeric keyboard. You can't use the keys across the top. So the number keys across the top and the numeric keyboard uses different codes, by the way. So you have to have a numeric keyboard. You hit Alt on your thing, and you type in 235. If you're running Windows Office or PowerPoint, Alt 235, it'll an Omega sign will pop up. But you have to enter the decimal equivalent because the PC. So if you wanted to do, we got some fractions we can do. So we got 1/2 and 1/4 on ASCII code. I mean on extended ASCII. So if I entered Alt 171, half would pop up there. Like I said, I can't do it on mine. Does that have a numeric keyboard on it? Yeah, it does. So yeah, if you were in Microsoft Office, if you was in Microsoft Word, I know the Omega sign works, and I know the Beta works. So Beta's on here somewhere. Yeah, Beta is 225. I know you can do that. I know you can do Alpha, which is 224. I know you can do Infinity. It's on here somewhere. Now, normally we don't use. This is where Unicode splits off. Unicode does not. They use their own codes for these things. They don't use this. So what the book calls EBCDEC is actually extended by ASCII. So that chart's in your textbook. There it is. Extended Binary Coded Decimal Interchange Code. So that's what EBCDEC stands for. IBM like to make big, long acronyms for their EBCDEC, Unicode. IBM, Microsoft Office uses a Unicode 16, which gives us 65,536 symbols and combinations. This is used by Microsoft Word. It's used by PowerPoint. It's used by Excel. It's used by the Internet. This 32, 2 to the 32nd, it gives us this many symbols. I've never seen anything that uses Unicode 32 right now. The biggest ones I've dealt with is Unicode 16. So this is what all your Microsoft products use to not only represent numbers and characters, but also control codes and everything else. So this is 8. Of course, Microsoft doesn't use this, and I don't have 16 up here because that'd be 65,536 combinations. So you can actually see it. You're up here typing on your keyboard, but what actually is being inserted so what actually is being inserted in your application is these codes. So this is 16 bits. So that character that I'm looking at now, that's pi. Now this is hex because it's 16 bits, so the character code would be out this far, but they give it to you in hexadecimal, right? Because it takes a lot less digits, even though it's a binary code. And it tells you right there that it's hexadecimal. And so yeah, so over there I'd use 375 decimal. Over here, the Omega symbol is 2126 hexadecimal. So they still use the lower 7-bit ASCII code in Unicode, but when it gets to all these special characters, by the way, Unicode, that's not true. All your icons, those little icons we can insert now, those use 32. So those suckers are going to be five characters long. I think they all start with 5. You know what I'm talking about? So when you put a smiley face on your computer now, we don't use this anymore. We actually have a 3D image of what emoticons is what they call it. Those are Unicodes, but they're not using Unicode 16. They're using I think they use 5 hex characters to send those. And you can look those up. And they keep adding, and they could go on, good gracious, forever. Think about it. Unicode 32 bit. That's 2 to the 32nd codes they can come up with. With 16, basically, that's every spoken language in the world, right? You'll understand that. That's 65,536 characters. So that's every written language, that we know of. So now you add more, then that's where we get into all those emoticons. And you can look up the codes, guys, if you want to. So your phone, we use emoticons all the time, right? How emotion, and that way you spell it, con? Codes. Code list. So here's all your emoticons, and every one of them's got a code. And so this uses, if you look at the codes, I think most of them start with 5. No, they don't show us the whole code. Let's see if they show us the whole code. They just put U plus. No, there it is. That's 5. 1, 2, 3, 4, 5. So that would be 4 bits, 32nd, 2 to the 36th codes that they're using so far. See, so right now they're using 5 digits, 1F600, and then you would get different ones depending on what you stick in right here. So Unicode right now is a so these are all your 3D emoticons that you use a lot when you text and stuff like that. And they do what every year? They keep adding to them, right? So used to you had a little group. Now on your iPhone, you do what? Takes you all to figure out one. Every once my granddaughter will just start sending emoticons to each other, texting, and then she'll send a bunch back. And so, but this is still Unicode. It's just instead of using 16 bits, they've expanded that now, and they're using that for these emoticons that we transmit back and forth. Okay, guys, I'll take a break, and we'll come back, and I'll give y'all's worksheet, and we'll work on that. So what time does the class get up? We'll work on that the rest of the class. And if you don't get through, you can do it at home, and you bring this back when we come back on. By the way, so everybody's done assignment 1, right? Assignment due is due this Friday at midnight, right? Okay. Then what else? I think that's only 2 assignments. We're having our first test next week. It's on the calendar, so I got your test up on your calendar. So our first test is going to be next week. I can't remember if it's Wednesday because Monday's a holiday, right? Monday's the 6th, yeah. So Monday's Labor Day, so our first test is going to be on the next Wednesday. We'll have a review. I'll put a written review up on Blackboard. And where would that be at? It'll be tests and reviews. There's a chapter. It'll be called Test 1 Review. So it'll be a written review. What I do on my reviews, there's going to be more on the test there's going to be more on the review that's on the test. And if you know everything that's on that review, you'll do real well on the test. If you find a mistake or something like that, you need to send me an email. And then if it's something important that I need to get out, I can send it out. I should be able to set up the texting application. Everybody's done the syllabus quiz. If you hadn't done the syllabus quiz, assignment one was due the first week, right? So odds are you got a 0 for assignment 1, but you can still get credit for the quiz as part of your grade. You can't get credit for assignment 1 because it's past due. If you don't send me this email by Friday using the format, now the format is so somebody sent me an email and they sent me multiple classes. I don't want the classes that you're taking this semester. I want you to start the subject. I want you to start the subject with ILT 194. And what happens is that instead of it going into my mail, I get about 50, 60 mails every day. It goes into a folder that's dedicated to this class. You can, but don't put a space. So don't type that next to, you just need to start the subject with ILT 194 with or without a space. Don't put an underscore, don't put anything like that. And I have it sorted by those 2 things. And in that way it automatically goes in, and it's got to start with that, and that's what I'm looking for. So if you don't get a reply email from me, odds are that means you have completed assignment, you have successfully completed assignment 2. Then what does that probably mean? That you did something wrong, and it probably went in my junk folder. It went somewhere else that I didn't find it, right? So all your email, when you send me email about this class, you're going to start it off with what? ILT number 194.